Good afternoon, everyone. So today we're going to look at acids and bases. So if you turn to page 18, 19 in your study material, page 19 has got all the definitions that you need to learn by heart. This is the way they're in the exam guidelines, so this is the way that you have to learn it and have to give it back. But it helps a lot if you understand what you're saying. So a lot of times today I'm going to ask you what's the definition, and then we're going to apply it. Because once you apply it and you understand it, then it's easier to learn the definition, right? Now, so let's, instead of looking at that page, start by looking at the second page. Right, that is page 20. Now on page 20, you find the table of all the acids and bases. See if we can find that. Right. All the acids and bases. Now, you can do nothing with acids and bases if you don't know this table by heart. You have to know hydrochloric acid is HCl and it is a strong one. Right. Nitric acid, HNO3, and it's strong. Sulfuric acid, H2SO4, there it is, and it's strong. So those three are your strong acids, and then all the rest is weak. So it's easy to remember which ones are strong, but you have to learn the formulas as well. Now, since grade 9, you've been learning the first three, because it's the strong ones, it's the important ones. You've learned all of them when you were young, and now we get on to more difficult ones, right? So the two that you might not be quite comfortable with is acetic acid, right? And you also now know that we can also call it ethanoic acid, acetic acid or ethanoic acid. And some of you will remember this because some of you learned it in grade 9, like CH3COOH. No. Yeah. So some of you know that one. That one is known to some of you. That's a weak one. The one I want to focus your attention on is that oxalic acid. Oxalic acid. That's actually one that is prescribed for your practicals. So you really have to know this because they ask it a lot, because they sometimes think you don't do the practical, you just write the report. So they want to test to see, did you do the practical? So they ask oxalic acid a lot. And what makes oxalic acid difficult is oxalic acid, you have COOH2. Now this looks really strange. Why 2 if it's the same thing? Now you've done organic chemistry at the beginning of the year, so you will be able to understand that it's got a carboxylic group to one side, and you've got the other carbon fixed onto that, and that's also got a carboxylic group to the other side. So if you look at this one, you've got 2 hydrogens over there, but you need to put the 2 there. They bonded together. It's not 2 separate ones. Otherwise, we could have just said COOH. Right. Now you have to say 2. So that's where the 2 come from. But this hydrogen and that hydrogen will be released equally easy. Right. It will be, if this one goes, that one usually goes as well. And therefore you are giving off 2. Right. So usually we prefer that top one, COOH2. But now some textbooks and sometimes even the Department of Education has started writing that the other way around so that it looks more like those. Now these bottom 2s, we call them organic acids because they've got a lot of carbon, hey? Right. So these ones are different. All the other ones are inorganic, and with them, if you give off an H, it is the one in front that's going. But when you get to organic acids, then it will be the H at the end that is leaving, right? So it's only those 2 that you have to learn by heart. They're organic, they do the things different, right? But then sometimes they take that one and they rewrite it that it looks like an inorganic one. And now when you have to write an equation, you can use either the top or the bottom formula. They will mark both, right? So Now you think, okay, I can only learn one. That's not the truth, because if you get into the exam paper, you don't know which formula will be used by the paper. You don't know if the department is going to use the top one or the bottom one. So actually, you have to learn both, right? Even if you prefer one, and I always prefer the top one. Right, that's the traditional way to write it. So you have to know both of them, right? Now, if you look at them, they are a little bit new, so let's talk about this. If you've got acetic acid, you've got CH3, COOH. If that H is removed, then you will end up with CH3, COO, negative, right? You are going to give off an H+. We'll talk about that just now. It's an acid. It's giving off an H+. If it H+ is removed, what remains is negative. And there's something else that goes wrong with acids and bases. You think the pluses and minuses are unimportant. If you leave out that minus, they leave out the mark, eh? Right. So remember, a plus or a minus is very important. A proton donor is going to give off an H+. So it will end up minus. Now, what is that called? What is that one? Acetic acid. Right. So what is the anion called? If that is acetic acid, then this is called acetate. Acetate. Right? So you can get sodium acetate or lithium acetate. So acetic acid gives you acetate ion. Right. And how about oxalic acid? If you've got oxalic acid, it's like that. It's going to give off both hydrogen. You end up with COO2. And what should be the charge? 2 minus, because you've given off 2H+. Right. And if this is called oxalic acid, what do we call this? Oxalate. Oxalate. Right. So acetic acid gives you acetate, and oxalic acid gives you oxalate. Right. So if you haven't learned that before, when you get to your second last page in your booklet, you will find that negative ions there, right? Oxalate and acetate. So if you are not comfortable with them, just go and look at them once again. Right. Okay, so you have to learn this table by heart, and also let's talk about the bases over here. Just 3, sodium, potassium, and lithium. The ones that will give hydroxides that dissolve completely. If you look at your periodic table, where do you find the lithium and the sodium and the potassium? Over there in group 1. Huh? And they are the ones that when you put them in water, they will dissolve. When you get to magnesium and calcium hydroxide, if you put them into water, they don't dissolve that fast. Now, actually, when you were in grade 10, you learned the table of solubility. But I know you can't remember it. Okay. So, just remember, sodium, lithium, and potassium hydroxide will immediately give off an OH minus because it dissolves, and therefore they are strong. And all the rest you have to learn, they are weak. And then we get to just one that looks strange. Which is the one that looks strange of the bases? NH3, ammonia. Now, ammonia is very important. Ammonia always do things different, right? You've got all the rules, and then you've got ammonia doing something different. So whenever you see ammonia, you have to say, okay, stop the bus. There's something different here, right? And we'll see what is different. So now I'm going to look at the bottom over there. We have a small table, and I'm actually going to redo the table to explain what's happening in this table. So you don't have to rewrite everything I'm going to write, okay? Everything is down there. You can make your notations of whatever you want to write on there. So we're going to look at acids and bases. And when we look at that, we are going to talk about strong acids and strong bases, and we are going to talk about weak acids and weak bases. Can you see it's exactly that table? Right. So you don't have to take too many notes. You can listen and you can try to understand rather. Okay, so let's talk about strong acids. Give me a strong acid. HCl, nice one, and HNO3 and H2SO4. Those are the 3 strong ones. Right, now back to my periodic table. I want you to check the hydrogen over there. Is it a metal or a non-metal? Remember, you've got that step. Hydrogen being on the right-hand side of the step is a non-metal. Okay, let's go on. How about chlorine? Chlorine, over there on the right-hand side, it is a non-metal. How about nitrogen? Non-metal. Oxygen, non-metal. Sulfur, non-metal. So everything you've got here is non-metals. Okay, and now I want to take you back to grade 10. If you've got non-metals, or grade 11, if you've got non-metals bonding, what type of bond will you have? Yes. You're actually good with remembering, hey? Covalent bonds, covalent bonds. If it's non-metal and non-metal, it makes a covalent bond. And how do you make a covalent bond? What happens when you make a covalent bond? It's sharing of electrons, right? So do they just overlap, and that electrons are now is part of both of them, right? They overlap. How does an ionic bond form? You give an electron over, and this one becomes negative, and that one is positive. You've got ions, right? So with covalent, do we have ions? No. So the important thing is if it's covalent, then there is no ions present in that one. So when this one reacts with water, the very important thing is you have to put water into your equation. I have to see water in my equation because it has to react with the water in order to make ions, right? What do we call the process of making ions? Ionize. So the acids will ionize. They are now going to produce ions, right? So they're going to produce ions. How are they going to produce ions? What is the definition of an acid? It's a proton donor, and a proton is an H+, right? So the proton is being donated. It's moving over. So what do we end up? With this one, you've got HCl. If it's giving off H+, it will end up as Cl-. Cl-, right, and actually in solution if you want to be thorough. Right, what happens to the water? It receives that H+, it's become H3O+ in solution, and we call that hydronium ion. Right, so you're fine with this one. So what is very important is here you have to have the water in the equation because it's got to ionize, it's got to make ions. Now look at the other side. Strong bases. What's your 3 strong bases? Sodium hydroxide, potassium hydroxide, lithium hydroxide. Okay, back to the periodic table. Lithium, sodium, potassium, what do you know about them? Metals, right? O and H, non-metals. So here you have metals and non-metals bonding together. So this is ionic bond. And you've already got ions. So when this one reacts with water, don't put water in the equation. It's not actually reacting with the water. It's sort of drifting on top, hey? Right, there's already ions present. It's not going to form ions, so it's not ionizing. What do we call it when we take things apart? Dissociate, right? Associate is when you put them together. Rain, weather, and pancake. Associate, right? If you take things apart, then it's dissociate. So what happens with bases is they dissociate. And how does it happen? So the sodium goes to one side and the OH to the other side, and they are in solution. Right. So that's why if you look back at page 19, If you turn back to page 19, there with the definitions we said, strong acids ionize completely in water to form high concentrations of H3. Weak acids ionize incompletely. So the word ionize there, because it only now I'm going to form ions. There were no ions present before. Right. Now let's go on to the weak acids. Name me a weak acid. Well, let's take acetic acid, which is the first one there. Right. Carbon, non-metal. Hydrogen, non-metal. Oxygen, non-metal. So all the weak ones, you will always also find they're covalent. So for the weak ones also, you need to put in water into your equation. And it will also now form ions, so it will now ionize. Right. And how does it ionize? By donating a proton, so you end up with CH3, COO minus. What is the name of this one? The acetate ion, right? If it was acetic acid, then you end up with the acetate ion. And obviously, hydronium ion. Okay, so if you add something to water, you will end up with something that's got charges. You end up with something that you've got ions. Right, now we get to the bases. Now there's a lot of bases. Which is our weird base? Ammonia. Right. Now all the other bases have got metals in them. It's like sodium carbonate, right? Or sodium hydroxide. They've got metals. What do you know about N? Where on the periodic table do I find nitrogen? Nitrogen is a non-metal, right? Nitrogen is a non-metal. And hydrogen? Non-metal. So this is the only base that is covalent, right? All the other bases that you use are ionic and they will dissociate, right? But when you get to NH3, this one is the weird one. It is our only covalent base. And what do we know about covalent things? There's no ions present. So when you react this one with water, for this one, you have to put water in your equation because this base is actually going to ionize. Right. All the others are going, bases are going to dissociate, but this one is going to ionize. How does a base react? A base is a proton acceptor, right? So it's going to receive a proton. So if it receives a proton, it will form NH4 plus. Remember, we receive an H plus. So there's another H making it 4, and the charge is plus. Right, in solution. And what happens to the water? There's an H plus removed. So that will end up as OH minus. Right. So we've got our equations. And now we haven't talked about strong and weak. What is the definition of a strong acid? And what's a weak acid? Strong acid, ionize completely. Completely. What does completely mean? It means if I put 1,000 HCl molecules into the water, they will all end up with H pluses. Every single one, right? Completely means everyone will be going over. So if I put 0.2 moles per cube decimeter in, I will end up with 0.2 cube moles per decimeter, right? If I put 1,000 in here, I will end up with 1,000 over there, right? But what do we know about weak? It ionizes incompletely, right? Incompletely. So if it is incompletely, it means I'm going to put 100,000 of that acetic molecules in, and I will find 4 or 5 have gone over and made H pluses, right? Only a few of them will react to give me H pluses. So this is difficult. We don't know how many are going over. Now let's look at the top one. Remember about Kc values? What will the Kc equation look like for that hydrochloric acid? It should have been Cl minus times H3O plus products divided by reactants, HCl. Right, no water. Why? Yes, solvent, right? It's a solvent. It's a pure liquid. It's a solvent. So the water doesn't come in there. Now, if you look at that one, is that going to have a big value or a small value? Big. Because what we said is everything is going over. So on that side, you have a big number. And on this side, you have more or less 0, right? So the top one is very big because it ionized completely. Most of it end up in the product form. So then the Kc, and now we call it Ka because it's acid. And it will be very big because most of the things end up dissociated, right? And in the same way, when you look at a weak one, the Ka value will be small because only a few of them produce H+. The rest is staying put in the same original way. Right. Strong bases dissociate completely, right? Means every single one will produce an OH minus. And weak ones, incompletely. Right. Now, if you look at the arrows, there's something that you can do with the arrows. If you look at the arrows, now the Department of Education don't mind if you put just a single arrow or double arrows or whatever. But for the guys who are going on with chemistry at university, it's nice to know there's a way that I can indicate that something is strong. If something is strong, I can indicate it by putting a big arrow to the right and a itsy-bitsy small one to the left. Right. Because most of the things will be doing that. Right. So a big arrow to the right and a small one to the left will show most of the things are going over. Right. And then how about a weak one? Then the itsy-bitsy one is to the right and the big one is to the left, showing you that the chemical equilibrium actually favors having more of these. Right. Okay. So this is the second one, the second table on that page. So I hope you all made your own notations over here. So remember, acids, they ionize, every single one of them. But when you get to the bases, it depends. All the others, like sodium carbonate, will still dissociate. But when you get to NH3, that is the weird one. It is the covalent base. And that one will ionize. So if you turn back to your definitions on the previous page, when we looked at acids, it was ionize and ionize because they were covalent, right? When you got to bases, what does it say about a strong base? Strong base, dissociate. That's what we expected, eh? Sodium hydroxide, lithium hydroxide, potassium hydroxide. They dissociate. But what does it say about weak bases? Dissociate and ionize. Who is responsible for the word ionize in that definition? NH3. It does things different because it's covalent, right? So now, when you know why the definition says that, then it's easier to learn that.